Actually, I would like to ask Eric a question if he's still around.
Yes.
So in your talk, there is this entanglement temperature. I'm just curious, like, to what extent is that entanglement temperature similar to the real temperature?
Can you hear me?
Can you hear me?
Can you hear me?
Yeah.
Yeah, we can hear you.
Okay.
Good.
In what sense? So the question is, in what sense the entanglement temperature, so this beta of X is similar to the real temperature? Is that your question?
Yep. Yeah.
Yeah, that's so let's say that in some sense, okay, the naive approach is that, look, the reduced density matrix is the mixed state, so it's kind of a thermal state, but it's not homogeneous, right? So the first thing is that is a temperature, even if can be interpreted as a temperature. First of all, this is a local thing, kind of local thing, because it depends on the position.
Yeah.
Second, this temperature, this beta of X, it's infinite, close to the end point. Yeah, I don't know. I think it's I don't have a full understanding of the similarity of the beta of X in the terms. This is the honest answer. There are features, similar features, but I would not say that a thermal state. So there are lucky situations like the one that Casini and Huerta Myers explored, where you can map the reduced density matrix into a term, right? It's a nice, beautiful result by Casini and Huerta Myers 2011, where they were able to map the reduced density matrix of a ball in a conformal theory into the thermal state in an hyperbolic geometry. But I'm not sure this is the most generic situation. I think, yeah, if you just change the geometry, then I don't know what remains of this picture. It's an interesting thing to explore from the quantum field theory point of view. Yeah, it's not satisfactory, but I know. Sorry.
Can I ask a question to?
Sure, go ahead.
To Phuc? So I was wondering, it's also a thermal question. So again, I'm curious because not really familiar with the details. But if I was to take a CFT in a thermal state, would there be an endpoint contribution?
It's an interesting question. So, well, of course, in our work, we only explored the vacuum state, excitations around the vacuum state. Well, so if you about exactly a thermal state or a perturbation away, some small perturbation away from the thermal
state. Let me motivate my question just a little bit, because I was just wondering about it, and I could be totally, off the mark here. But usually, if I'm usually thinking the Euclidean picture, and if I, perturb a CFT Lagrangian by the stress tensor, by adding the stress tensor, the coupling, the coefficient of that is basically a chemical potential for the stress tensor. It's a chemical potential for energy, which means it's a temperature. So since you were discussing perturbations by the stress tensor, I was just wondering if such a perturbation can be viewed locally as a change in some kind of local notion of temperature, and whether therefore, the effects that you see as an endpoint contribution also appear at finite temperature. But like I said, totally off the mark. It could be just wondering about it. So
yeah, I think it's an interesting question. I'm not sure I have something very insightful to say off the top of my head. Yeah. But clearly, if it's just a thermal state without any perturbation, then the modular Hamiltonian, let's see, is just a local integral of the stress tensor of the kind that Eric Tony just discussed. And so if it's just a thermal state, then clearly I think there is no endpoint contribution.
Okay.
Perturbations away from on top of a thermal state. I will have to think a bit about that.
Yeah, I guess the question was more about just the thermal state per se, because I mean, most likely you will also find endpoint contributions if you put perturbations on top of the thermal state. But I was curious just about the thermal state alone.
Yeah, so it seems to me that if it's just a thermal state, then there will not be an endpoint contribution.
Okay.
Because it's the modular Hamiltonian is just the integral of the stress tensor with some kernel function.
Correct. Okay.
Yeah, but I think you have an interesting interpretation, and I will have to think a bit about this.
Yeah. Thanks.
Okay, are there any more questions for any other speaker? Or if the speakers have any questions?